is 3E-4, which is a pretty good default for most optimizations that you want to run at a very early debugging stage. So this is our simple inner loop, and we are overfitting a single batch, and this looks good. So now what comes next is we don't just want to overfit a single batch, we actually want to do an optimization. So we actually need to iterate these XY batches and create a little data loader that makes sure that we're always getting a fresh batch and that we're actually optimizing a reasonable objective. So let's do that next. Okay, so this is what I came up with, and I wrote a little data loader light. So what this data loader does is we're importing the token up here, we're reading the entire text file from this single input.txt, tokenizing it, and then we're just printing the number of tokens in total and the number of batches in a single epoch of iterating over this dataset. So how many unique batches do we output before we loop back around to the beginning of the document and start reading it again? So we start off at position 0, and then we simply walk the document in batches of b times t. So we take chunks of b times t and then always advance by b times t. And it's important to note that we're always advancing our position by exactly b times t. But when we're fetching the tokens, we're actually fetching from current position to b times t plus 1. And we need that plus 1 because, remember, we need the target token for the last token in the current batch. And so that way we can do the XY exactly as we did it before. And if we are to run out of data, we'll just loop back around to 0. So this is one way to write a very, very simple data loader that simply just goes through the file in chunks and is good enough for us for current purposes. And we're going to complexify it later. And now we'd like to come back around here, and we'd like to actually use our data loader. So the import tick token has moved up, and actually all of this is now complexify it later. And now we'd like to come back around here, and we'd like to actually use our data loader. So the import tick token has moved up, and actually all of this is now useless. So instead we just want a train loader for the training data. And we want to use the same hyperparameters for 4. So batch size was 4 and time was 32. And then here, we need to get the XY for the current batch. So let's see if Copilot gets it, because this is simple enough. So we call the next batch, and then we make sure that we have to move our tensors from CPU to the device. So here, when I converted the tokens, notice that I didn't actually move these tokens to the GPU. I left them on the CPU, which is the default. And that's just because I'm trying not to waste too much memory on the GPU. In this case, this is a tiny data set and it would fit, but it's fine to just ship it to GPU right now for our purposes right now. So we get the next batch, we keep the data loader simple CPU class, and then here we actually ship it to the GPU and do all the computation. And let's see if this runs. So Python train GPT 2.py. And what do we expect to see before this actually happens? What we expect to see is now we're actually getting the next batch. So we expect to not overfit a single batch. And so I expect our loss to come down, but not too much. And that's because I still expect it to come down because in the 50,257 tokens, many of those tokens never occur in our dataset. So there's some very easy gains to be made here in the optimization by, for example, taking the biases of all the logits that never occur and driving them to negative infinity. And that would basically it's just that all of these crazy Unicodes or different languages, those tokens never occur, so their probability should be very low. And so the gains that we should be seeing are along the lines of basically deleting the usage of tokens that never occur. That's probably most of the loss gain that we're going to see at this scale right now. But we shouldn't come to a zero because we are only doing 50 iterations, and I don't think that's enough to do an epoch right now. So let's see what we got. We have 338,000 tokens, which makes sense with our 3-to-1 compression ratio because there are 1 million characters. So one epoch with the current setting of B and T will take 2,600 batches. And we're only doing 50 batches of optimization in here. So we start off in a familiar territory, as expected, and then we seem to come down to about 6.6. So basically, things seem to be working okay right now with respect to our expectations. So that's good. Okay, next, I want to actually fix a bug that we have in our code. It's not a major bug, but it is a bug with respect to how GPT-2 training should happen. So the bug is the following. We were not being careful enough when we were loading the weights from Hugging Face, and we actually missed a little detail. So if we come here, notice that the shape of these two tensors is the same. So this one here is the token embedding at the bottom of the transformer, right? So, and this one here is the language modeling head at the top of the transformer. And both of these are basically two-dimensional tensors, and their shape is identical. So here, the first one is the output embedding, the token embedding, and the second one is this linear layer at the very top, the classifier layer. Both of them are of shape 50,000 to 57 by 768. This one here is giving us our token embeddings at the bottom, and this one here is taking the 768 channels of the transformer and trying to upscale that to 50,000 to 57 to get the logis for the next token. So they're both the same shape, but more than that, actually, if you look at comparing their elements, in PyTorch, this is an element-wise equality, so then we use .all, and we see that every single element is identical. And more than that, we see that if we actually look at the data pointer, this is a way in PyTorch to get the actual pointer to the data and the storage. We see that actually the pointer is identical. So not only are these two separate tensors that happen to have the same shape and elements, they're actually pointing to the identical tensor. So what's happening here is that this is a common weight time scheme that actually comes from the original Attention is All You Need paper, and actually even the reference before it. So if we come here, embeddings and softmax in the Attention is All You Need paper, they mentioned that in our model, we shared the same weight matrix between the two embedding layers and the pre-softmax linear transformation similar to 30. So this is an awkward way to phrase that these two are shared and they're tied and they're the same matrix. And the 30 reference is this paper. So this came out in 2017. And you can read the full paper, but basically it argues for this weight tying scheme. And I think intuitively the idea for why you might want to do this comes from this paragraph here. And basically, you can observe that you actually want these two matrices to behave similar in the following sense. If two tokens are very similar semantically, like maybe one of them is all lowercase and the other one is all uppercase, or it's the same token in a different language or something like that, if you have similarity between two tokens, presumably you would expect that they are nearby in the token embedding space. But in the exact same way, you'd expect that if you have two tokens that are similar semantically, you'd expect them to get the same probabilities at the output of a transformer because they are semantically similar. And so both positions in the transformer at the very bottom and at the top have this property that similar tokens should have similar embeddings or similar weights. And so this is what motivates their exploration here. And they kind of, I don't want to go through the entire paper, and you can go through it, but this is what they observe. They also observe that if you look at the output embeddings, they also behave like word embeddings. If you just kind of try to use those weights as word embeddings. So they kind of observe this similarity, they try to tie them, and they observe that they can get much better performance in that way. And so this was adopted in the attention is all you need paper, and then it was used again in GPT-2 as well. So I couldn't find it in the transformer implementation. I'm not sure where they tie those embeddings, but I can find it in the original GPT-2 code introduced by OpenAI. So this is OpenAI GPT-2 source model. And here where they are forwarding this model, and this is in TensorFlow, but that's okay, we see that they get the WTE token embeddings. And then here is the encoder of the token embeddings and the position. And then here at the bottom, they use the WTE again to do the logits. So when they get the logits, it's a matmul of this output from the transformer, and the WTE tensor is reused. And so the WTE tensor basically is used twice on the bottom of the transformer and on the top of the transformer. And in the backward pass, we'll get gradients contributions from both branches, right? And these gradients will add up on the WTE tensor. So we'll get a contribution from the classifier layer, and then at the very end of the transformer, we'll get a contribution at the bottom of it, floating again into the WTE tensor. So we are currently not sharing WTE in our code, but we want to do that. So weight sharing scheme. And one way to do this, let's see if Copilot gets it. Oh, it does. Okay. So this is one way to do it. Basically, relatively straightforward. What we're doing here is we're taking the WTE.weight and we're simply redirecting it to point to the LM head. So this basically copies the data pointer, right? It copies the reference. And now the WTE.weight becomes orphaned, the old value of it, and PyTorch will clean it up. Python will clean it up. And so we are only left with a single tensor, and it's going to be used twice in the forward pass. And use this, and this should probably train. So we should be able to use this, and this should probably train. We're just going to basically be using this exact same sensor twice, and we weren't being careful with tracking the likelihoods, but according to the paper and according to the results, you'd actually expect slightly better results doing this. And in addition to that, one other reason that this is very, very nice for us is that this is a ton of parameters, right? What is the size of here? It's 768 times 50,257. So this is 40 million parameters. And this is a 124 million parameter model. So 40 divide 124. So this is like 30% of the parameters are being saved using this weight time scheme. And so this might be one of the reasons that this is working slightly better. If you're not training the model long enough, because of the weight tying, you don't have to train as many parameters. And so you become more efficient in terms of the training process because you have fewer parameters and you're putting in this inductive bias that these two embeddings should share similarities between tokens. So this is the weight tiring scheme, and we've saved a ton of parameters, and we expect our model to work slightly better because of this scheme. Okay, next, I would like us to be a bit more careful with the initialization and to try to follow the way GPT-2 initialized their model. Now, unfortunately, the GPT-2 paper and the GPT-3 paper are not very explicit about initialization, so we kind of have to read between the lines. And instead of going to the paper, which is quite vague, there's a bit of information in the code that OpenAI released. So when we go to the model.py, we see that when they initialize their weights, they are using the standard deviation of 0.02. And that's how so this is a normal distribution for the weights, and the standard deviation is 0.02. For the bias, they initialize that with 0. And then when we scroll down here, why is this not scrolling? The token embeddings are initialized at 0.02, and position embeddings at 0.01 for some reason. So those are the initializations, and we'd like to mirror that in GPT-2 in our module here. So here's a snippet of code that I sort of came up with very quickly. So what's happening here is at the end of our initializer for the GPT module, we're calling the apply function of NN module, and that iterates all the submodules of this module and applies init weights function on them. And so what's happening here is that we're iterating all the modules here, and if they are an nn.linear module, then we're gonna make sure to initialize the weight using a normal with a standard deviation of 0.02. If there's a bias in this layer, we will make sure to initialize that to 0. Note that 0 initialization for the bias is not actually the PyTorch default. By default, the bias here is initialized with a uniform, so that's interesting. So we make sure to use 0. And for the embedding, we're just going to use 0.02 and keep it the same. So we're not going to change it to 0.01 for positional because it's about the same. And then if you look through our model, the only other layer that requires initialization and that has parameters is the layer norm. And the PyTorch default initialization sets the scale in the layer norm to be 1 and the offset in the layer norm to be 0. So that's exactly what we want, and so we're just gonna keep it that way. And so this is the default initialization if we are following the the GPT-2 source code that they released. I would like to point out, by the way, that typically the standard deviation here on this initialization, if you follow the Javier initialization, would be 1 over the square root of the number of features that are incoming into this layer. But if you'll notice, actually, 0.02 is basically consistent with that, because the D-model sizes inside these transformers for GPT-2 are roughly 768, 1600, etc. So 1 over the square root of, for example, 768 gives us 0.03. If we plug in 1600, we get 0.02. If we plug in 3 times that, 0.014, etc. So basically 0.02 is roughly in the vicinity of reasonable values for these initializations anyway. So it's not completely crazy to be hard coding 0.02 here, but you'd like typically something that grows with the model size instead, but we will keep this because that is the GPT-2 initialization per their source code. But we are not fully done yet on initialization because there's one more caveat here. So here, a modified initialization which accounts for the accumulation on the residual path with model depth is used. We scale the weight of residual layers at initialization by a factor of 1 over square root of n, where n is the number of residual layers. So this is what GPT-2 paper says. So we have not implemented that yet, and we can do so now. Now, I'd like to actually kind of like motivate a little bit what they mean here, I think. So here's roughly what they mean. If you start out with dual stream is of this form where we continue adding to it. X is X plus something, some kind of contribution. So every single block of the residual network contributes some amount, and it gets added. And so what ends up happening is that the variance of the activations in the residual stream grows. So here's a small example. If we start at 0, and then we, for 100 times, we have sort of this residual stream of 768 zeros. And then 100 times we add random, which is a normal distribution, 0 mean, 1 standard deviation. If we add to it, then by the end, the residual stream has grown to have standard deviation of 10. And that's just because we're always adding these numbers. And so this scaling factor that they use here exactly compensates for that growth. So if we take n and we basically scale down every one of these contributions into the residual stream by 1 over the square root of n. So 1 over the square root of n is n to the negative 0.5, right? Because n to the 0.5 is the square root, and then 1 over the square root is n negative 0.5. If we scale it in this way, then we see that we actually get 1. So this is a way to control the growth of activations inside the residual stream in the forward pass. And so we'd like to initialize in the same way, where these weights that are at the end of each block, so this cproj layer, the GPT paper proposes to scale down those weights by 1 over the square root of the number of residual layers. So one crude way to implement this is the following. I don't know if this is PyTorch sanctioned, but it works for me, is we'll do in the initialization, see the that special nano GPT scale init is 1. So we're setting kind of like a flag for this module. There must be a better way in PyTorch, right? But kind of like a flag for this module. There must be a better way in PyTorch, right? But I don't know. Okay, so we're basically attaching this flag and trying to make sure that it doesn't conflict with anything previously. And then when we come down here, this STD should be 0.02 by default. But then if has utter module of this thing, then std times equals, Copilot is not guessing correctly. So we want 1 over the square root of the number of layers. So the number of residual layers here is twice times self.config layers, and then this times negative 0.5. So we want to scale down that standard deviation, and this should be correct and implement that. I should clarify, by the way, that the 2 times number of layers comes from the fact that every single one of our layers in the transformer actually has 2 blocks that add to the residual pathway, right? We have the attention and then the MLP. So that's where the 2 times comes from. And the other thing to mention is that what's slightly awkward, but we're not going to fix it, is that because we are weight sharing the WTE and the LM head, in this iteration over all submodules, we're going to actually come around to that tensor twice. So we're going to first initialize it as an embedding with 0.02, and then we're going to come back around it again in a linear and initialize it again using 0.02. And it's going to be 0.02 because the LM head is, of course, not scaled, so it's not going to come. Come here. It's going to be basically initialized twice using the identical same initialization, but that's okay. And then scrolling over here, I added some code here so that we have reproducibility. To set the seeds, and now we should be able to Python train GPT2.py and let this running. And as far as I know, this is the GPT-2 initialization in the way we've implemented it right now. So this looks reasonable to me. Okay, so at this point, we have the GPT-2 model. We have some confidence. That it's correctly implemented, we've initialized it properly, and we have a data loader that's iterating through data batches, and we can train. So now comes the fun part. I'd like us to speed up reasonable to me.